Now we are welcoming Safe Wheels. Kaja and Roksana are going to present the project of the team, which is called Intelligent Laser System to Increase Safety of Cyclists at Junctions. Thank you so much.
Did you ever ride a bike?
Me and Kaja are both passionate cyclists and we often go to universities by bikes. But we are scared that one day something like this will happen to us.
We are scared. Aren't you scared as well?
I'm sure that some of you said yes in your head. That's why our team provided a solution just for you. Our team, Safe Wheels, invented intelligent laser system to increase safety of cyclists at junctions. Bicycle is a mean of transportation that is strongly encouraged in the European Union because it is seen as healthy and eco-friendly alternative to cars. But as you all know, cyclists are one of the most vulnerable members of traffic. In case of accidents with cars and trucks, they are the ones that suffer the most, and often don't survive. That's in European Union, only in 2016, around 2,000 people died on the roads because of the accident on the bike. Our mission is to improve safety of cyclists at junctions by reducing the number of accidents involving cyclists and developing a system that will warn car drivers of oncoming cyclists.
Every team needs brilliant mentors. And because of that, we decided to work with three amazing academics from Poland, from Silesian University of Technology in Katowice, and from France, from National Institute of Applied Sciences in Toulouse. First of our mentor is double PhD student Agata Raczyńska. Her work mostly concentrates in the field of biodegradation of synthetic polymers. Our main mentor is Tomasz Pawlik, PhD. He's professor, ceramic materials professor at our department in Katowice. He has tons of experience in working with PBL projects. And the last of our mentor is Jakub Smoleń. He's also a PhD student, and his work is mostly concentrated in the field of degradation and recycling of problematic materials. I think that two of our mentors, Tomasz Pawlik and Jakub Smoleń, are familiar to you. And you are right, they were mentors of the last year's winning team, New Cycle. As you already know our mentors, it's time to get to know us, mentees. We are a combination of students from Poland, from Silesian University of Technology, and from Italy, from one of the best universities in the world, Politecnica di Milano. Roksana Sornat is the team leader of our team, and me, Kaja Orzechowska, I'm the co-leader. Together with Klaudia Gładyś and Mrowiec, we are from Poland, and the male part, Ziad and Tommaso Ansaloni, are represented in Italy. We decided to work on everything together, but each task had its own captain. For example, Roksana coordinated all of our work, and I was responsible for composition of material.
When we already knew the challenge that we want to work on, we decided to identify the problem. First of all, we did a couple of brainstorming sessions, both online and offline, with our team members. We decided that we want our design to be inclusive and we want to focus on circular economy. Then we did public consultation sessions with disabled and fully able cyclists, our family members, friends, people that work at our universities. Then we collected statistical data from both European and national sources. When we collected the data, we looked at it and we've seen that around 20% of all fatalities that happen during cyclist accidents are during night. Then we decided to look on the type of roads where the accident happened, and we looked and we saw that around 17% of all accidents that happened in Europe happen at junctions. But as you can see on the slide, in most Western Europe countries, it's even more, up to 44% in Netherlands. Then we also looked for the reasons why the accidents happen. In Poland, it's failure to give the right of way and improper crossing of the bicycle lane.
As you already heard about the way we thought the way we identified the problem. After brainstorming, public consultations, and the statistical analysis, we highlighted three main challenges and problems that we know we are able to fully solve. First is the low visibility of cyclists, mostly in the night, but also in bad weather conditions. But we also were thinking about disabled cyclists, hand cyclists, and about children. Their height is lower, so they are not as visible as adults. The second one is the lack of sufficient safety measures on the road. You can see that sometimes the bicycle lanes, they look just like a maze. The last one is the lack of protective equipment. I'm not talking about just wearing helmets. I'm talking that sometimes it's just not enough. From the statistical analysis and from all our problem identification, we wanted to focus on the junction problem. You can see that the car driver is unable to see the upcoming cyclist from the other side of the building, from around the corner. So we did this in our case study in the controlled and safety environment. Everybody knew what's going to happen. And as you can see, the car driver, they are not able to give the right of the way.
When we knew what kind of problem and what kind of situation we want to deal with, we decided to do a schematic of our solution. Our solution is combined out of a couple of elements. First of all, we have a safe wheels bump and a laser that emits the laser beam. When a cyclist is going through the cyclist road, it goes through the speed bump, to the safe wheels bump, and the laser is turned on. The laser emits the laser beam that informs the car driver about oncoming cyclists.
We are thinking with circular economy in mind. As we are mostly materials engineering students, so we wanted to create the new solution. We are looking through the market and we couldn't find anything that we are looking for. So we decided to create it with using only waste materials. Firstly, we decided to use waste car tires and bicycle tires. We shredded them and washed. Then we added resin, but not just resin. Terephthalic resin made out of waste PET bottles. Then chemical processes happened like cross-linking and curing, and after everything, we had ready-to-use safe wheels bump. So we can see that we combined two main recycling techniques. First, chemical decomposition for the waste PET bottles, and mechanical decomposition for the waste tires. Looking closer to geometry of our safe wheels bump, I need to say that it was designed in all European Union norms and standards in mind. So it has 10 millimeters. It's enough to protect our piezoelectric sensor, touch sensor, that it's inside of this. And it's also not high, so it's not affecting the cyclists. They're unable to feel it. So we created completely new material and completely new product. We needed to test this. We provided a few main tests. First, compression strength test. Our material can resist the force of 4.4 megapascals, which is equal to 4 trucks. So basically, I'm sure it will survive the weight of the cyclist. Second one is the hardness. Our material has 61D shore hardness, so it's like shopping cart wheels. Then our material is frost resistant. It has anti-icing surface, and because of that it's completely made out of waste, it's cost efficient.
Okay, so we knew what we want to do. We bought our equipment, we also made a safe wheels bump, and we decided to test if the solution works in the safety environment of our faculty. Here you can see that the cyclist is going through the safe wheels bump and the laser system is activated. We did this test at daytime and at nighttime. And as you can see on the slide, on the right side, the safe wheels system is even more effective at nighttime and in the bad weather conditions. Okay, so we knew that our system is working, so we decided to go big and test the system with cars. Here you can see the same situation as you saw a couple of slides before. You can see that the cyclist is going through the speed bump, and this system is activated. The car is stopping because it sees that something is going from the left side of the road. And after the system turns off, the car can go to its destination, and the cyclist is not bothered by it. About the effectiveness of our system. First of all, it enhances the visibility of the cyclist, even if the height of the cyclist is lower due to this using handbike or if it's a kid. Then it has inclusive design. It can be used by anyone, by disabled people, fully able people, people from all age groups, kids, adults, elderly people. Then it has potential accident reduction. If it was introduced in 2016, it could lead to 400 people be with us still to this day. Then the system is also user-friendly. You don't have to have any kind of courses to use it. You just have to go through the bicycle lane like you usually would, and it's increasing the safety of your road. Then the system uses adaptive technology. It adapts to the weather conditions that is all around it, and it works even better in the hard weather conditions.
So we did it. We succeeded, of course. We created a completely new system, completely new material that is completely made out of waste.
Our laser is certified.
Weather doesn't affect our system.
It has inclusive design.
There's no additional cost for the end user.
And the use of our product is intuitive. And now we would like to leave you with a quote by Judy Rell that was with us through the months of creating the safest system. At the end of the day, the goals are simple: safety and security. And our solution is just like that. Thank you so much.
Thank you very much for your presentation. Now, Professor Asadi is going to start.
Okay, thank you so much. What plans do you have for future improvement or enhancement to your solution? How do you see it evolving to meet the changing needs of bike riders and advancements in technology?
Okay, first of all, we would like to implement it in a real life scenario, not in our faculty site, so we could see if it really improves the safety of the cyclists on the roads in the real life scenario with real cars, with real cyclists, and if it's as good as we think it will be and as we tried it on ourselves.
So I need to tell you that I'm really excited, but we were already talking with our city council, and they are willing to test our system in Katowice.
In our city.
Yes, in our city. Can you repeat the last part of the question?
The last part is, how do you see the evolving to meet the changing needs of bike riders and advancements in technology?
Okay, so I told you about the height of our bump. I didn't tell you about its length. It can be adjusted to all the roads, and also the system is easily programmed, so it's also adjusted to roads for the amount of time it requires for the cyclist to pass the road.
Yeah. Here on the video it was just like 3 or 4 seconds, but if the crossing is longer,
Right.
then you can program the system to also work for longer time. And also if we do like a real life consultation with also elderly people, elderly cyclists, then we can make the time frame longer, for example. Yeah.
Thank you.
Thank you.
Thank you very much. Professor Patrisanos, you're going to ask.
And thank you. Congratulations for your presentation. Very dynamic and very so it's a real problem, yes, yeah, actually. And I would like to know about the sensor you will use to the response of the going on the bicycle.
Okay.
How many sensors and how the signal will be transmitted to the.
Okay, so we decided to use piezoelectric touch sensor. with few of them in the bottom of our cyclist bar. They are in the middle part, and two of them are at the side. For like the perfect, for like no matter which part of the cyclist will like decide to cross, he doesn't need to walk right the middle part. He can ride this side or something.
Yeah, but the amount of sensor depends on the language. Also, we can't tell you what kind of sensor specifically we use because it's like our know-how. So, yeah.
Okay, thank you.
Thank you.
Yeah, I wouldn't go for any question because everything was quite clear, but can you give us a cost of the system? How much will it cost for a single lane?
Of course. The cost of our system is around 1,000 euros. In zlotys, it's 5,000 in zlotys. So just a bit above 1,000 euros.
Sure. Thank you.
Thank you so much.
I was going to ask that question because I find actually it's cheap. I think
Yes, the main cost is the laser.
the idea would be very successful.
Yes, because we use the waste material.
Especially in Amsterdam.
Yeah.
Yes.
So I don't have any questions because
Okay.
the system is very simple. The idea is brilliant. So thank you very much.
Thank you so much. Thank you for your attention.